So yes, today I will present to you the bulk of the work that I've been doing since I started my PhD here, which has been dedicated to the study of galaxies inside cosmic voids. So to start with the bigger picture of the setting of this work, I wanted to give a brief introduction of the bigger picture of this. So our current understanding of how the universe works is that galaxies do not live isolated as islands in the big empty universe. They are organized in a pattern, which is these large-scale structures that is created and shaped by gravity. This is arranged in a thread-like structure, which is why we call it the cosmic web. And inside this very big structure that can be observed, has been observed both in real data and in simulations. Many different components live, so which vary on the widest range of scales. We go from tiny galaxies to groups of galaxies, then to clusters of galaxies, to filaments that connect to the clusters, and then to walls, and in the end to voids, which are the biggest structures in the cosmic web. So why it is interesting to study this large-scale structure? The observation and the study of simulation of the large-scale structure can lead us to better constraining our models that describe our understanding of the universe, both on a cosmological level, so to study the effect of dark matter and dark energy on shaping the large-scale structure, and to test the evolutionary path of galaxies living in all these different kinds of environments. So today I will focus on voids, as I was telling before, which is in fact the largest structures in our universe. So cosmic voids are vast expanses of space that, despite their name, they're not empty. The galaxies do live inside them, and it is interesting to wonder and to study how they ended up there, and how the voids came to be. Since they are characterized by very low density, voids are expected to expand over time due to the lower gravitational pull that characterizes them, and therefore they are thought to be the dominant volume fraction of our present universe. And galaxies that live inside them are expected to have a very different evolutionary paths than galaxies that live in the denser regions of our universe. So that's why the voids are perfect laboratories for studying galaxy evolution. So in the effort of trying to answer the central question, one could follow many different paths, because environment and galaxy properties and evolution are intrinsically linked together. So because galaxies live in lower density environments, they are expected to have fewer interactions with the other galaxies, and so we could study their morphology, for example, how their morphology is affected by the fact that they don't interact with galaxies, and also how their star formation changes because they do their evolution on their own in their isolated space. So to study voids, we need to find them first, and that is quite a challenge, because as I was saying before, they are very rare and vast, extended structures. So to build a good enough statistic, we need a large area, or a survey with a large area to observe at least some of them, to do some statistics. But also we need a survey that is deep enough to be sensitive to extremely faint systems, so that we can reconstruct the environment correctly, because of course, not every filament and every small point of the density field can has the same luminosity, of course. So we need to be sensitive to fainter structure to have a high enough statistic of tracers. Of course, with a spectroscopic survey, a spectroscopic survey is essential to pinpoint with high precision the position of galaxies, and to make an effective 3D mapping of the universe, and to identify correctly voids. And also, of course, since we're interested in the evolution of the universe, it's good to have a survey with a wide redshift range so that we can also compare voids at different stages of the age of the universe. And this is why our main, the instrument that we will use for this project is Euclid, because it sort of summarizes all of these qualities in the same instrument. So most of you know Euclid. It's a satellite, it's a mission of the European Space Agency. It launched almost 2 years ago now, and it started observing in February 2024. There was recently a quick release, public quick release of data and of papers of the consortium. But even bigger releases of data will be coming in the next few years. So over the 6-year mission, Euclid will carry out 2 surveys: the wide, which is outlined here by the blue contours, and the deep survey. The wide survey, it's, as the name says, is the widest coverage of the mission. It will be 14,000 degrees of extragalactic sky. And the deep survey will still be pretty large. And there will be split in 3 fields, north, south, and fornax. And it will be a total of 53 square degrees of very deep observations. And so Euclid will, at the end of its 6-year mission, will create an atlas of the sky, and it will help constraining both cosmology and galaxy evolutionary studies. So this brings me to the actual start of this talk, which is the project that I've been working on during my PhD, which is linked to the study of properties and evolutions of galaxies and cosmic voids in preparation for Euclid-like simulations for DR1, which will be the first public data release that will happen at the end of next year. So Euclid-like, what do we mean when we say Euclid-like simulations? The data that we're analyzing now is mock lightcones. So the lightcones that are made to reproduce what we think we expect to observe in a Euclid survey. So the lightcone is modeled with the Gaia semi-analytic model, which is a galaxy evolution and assembly model, which is has been developed in Trieste. So semi-analytic model, very briefly, combine the dark matter simulation, the dark matter only simulations of the universe. So the merger between dark matter halos that build the merger trees of galaxies over time, and the recipes for galaxy formation. So galaxies are fed into these dark matter halos, and then they evolve according to their merger between halos and to the way that galaxies evolve through time. So star formation and on all the different recipes that entail galaxy formation and evolution. And these two together provide us with lightcones, which is this catalogs of galaxies that span across redshift ranges. And for this study, we have tailored the Gaia lightcone to reproduce the Euclid Deep Survey at the epoch of DR1. So what we expect to see basically next year in the data in the first data release. So we cut the redshift range between 0.4 and 0.8 because we are selecting galaxies that have an H-alpha flux sensitivity greater than 10 to the minus 17. So we are selecting galaxies that emit H-alpha, and H-alpha is visible within the Euclid redshift range between these two redshifts. We also have other assumptions that relate to the spectroscopic sampling rate that is expected, and the interloper fractions, which is a catastrophic redshift errors. So this is the data set that we're starting with. So then how do we find voids in this data set? We have, over this past year, considered a lot of different algorithms. This is the summary of everything that we have considered up till now. You can see that they are grouped between in different categories because there are a lot of algorithms around that that analyze the environment, because only a few of these are tailored to find voids. Some of them, just like, for example, disperse or BMC, have been designed to study peaks or filaments of the cosmic web, and so voids are a byproduct. So it's interesting to compare the voids as being a byproduct of these codes. The one we're starting with is Revolver, which is a 3D which is based on 3D Voronoi tessellation. So that's why we assume that we have spectroscopic redshift, because we assume that the highest precision on the z-axis of the lightcone. So the Revolver algorithm is based, as I was saying, on the tessellation of the lightcone with Voronoi, and on the watershed transform, which is very briefly very briefly, it's a mathematical concept that fills the areas of low density from the local minimum. So it finds the minima inside the lightcone, the density minimum of the density field, and fills the water, so watershed transform, until the ridges of the density field, and then defines regions as void region or and that. And so we have a void catalog associated to the lightcone catalog that I was telling you about before. This is what we see with Revolver. These are the voids that Revolver finds. So you can see on the y-axis is the number of galaxies inside each void, and on the x-axis is a radius, sphere-sized radius, because voids are not spheres in this assumption. Voids are collection of polyhedra of Voronoi. So we assume that the radius, the sphere-sized radius, is the equivalent of a sphere of the volume of the void. And so this was just to highlight the fact that the size of voids correlates with redshift, of course, because both of the evolution of the universe, but also because the lightcone is bigger at higher redshift, and also regarding to the evolution of redshift, we notice that we see larger voids at higher redshift, but we also see that at fixed radius, voids at higher redshift appear to be containing fewer galaxies. This is due to our selection of the traces, actually. So it's due to the fact that we select in its alpha flux, so at lower redshift, we are more sensitive to the smaller structures. So we both detect smaller voids and we populate more the larger ones. So since we are interested in the galaxies inside voids, we will have a look now at the properties of the galaxies that are found inside these voids. To parameterize the environment, we have again considered a lot of different parameters, and I will show today this parameter, which is the distance of the galaxy from the center of its related void divided by the size of the void. So a normalized distance from the center of the under density. We use this distribution to find the median, which we identify as sort of an inside-outside of our void environment, and then we subdivide everything that is below the median in quantiles of 10%, in percentiles of 10%, and we plot the cumulative distribution of galaxies of galaxies in these 5 environments, and also this control sample outside the median, the cumulative distribution of the specific star formation rate of the galaxies. You can see that in the zoom in, you can see better that how the lowest densities are the most different between the three. So they are very shifted to higher specific star formation rates. This is the lowest redshift bin, so this means that at low redshift, galaxies inside voids are more star forming than galaxies at the highest densities. So you can see here also the dispersion of, because we repeat these. Yeah, sorry, I didn't mention that fact that these distributions are mass matched. So every sample in these environments has the same distribution of mass. So we have removed the correlation between with the stellar mass. So, and the dispersion that you see here is just a repetition of the mass matching, which randomly extracts galaxies from the sample. So, if we look at the of all the redshift bin that we use, and we keep in mind that the evolution of the universe goes in this direction, from right to left, you can see that looking at the zoom-in plots, there is an inversion of the trend between the lowest densities and the highest densities. So this doesn't mean that there are more passive galaxies at the lowest densities at high redshifts, but it means that the universe evolved in a way that the environment at some point in this redshift range started affecting the star formation of the galaxies. So while star-forming galaxies were more common at a higher density in the earlier universe, as the universe evolves, you can see that the star formation rate is still very effective in the low densities, while the other ones have shifted to lower specific star formation rates. So galaxies have become more passive in the highest densities. And another thing that we can have a look at here is also the effect of the structure galaxies are living in. So the size of the void, basically. So if before we were looking at total distribution, now the plots on the upper side of the slide represent galaxies inside small voids, and these one are galaxies inside larger voids. The redshift bin are the same, so this is very low redshift and this is very high redshift inside our redshift range. And you can see that at low redshift, the specific star formation rate is driven by galaxies that inhabit small voids. So there are more star-forming galaxies inside small voids at low redshift. While at the other side of the spectrum of redshift, the evolution of specific star formation rate is driven by galaxies in large voids at higher redshift. So the last thing that I wanted to show today is related to how galaxies build up their mass, and specifically how they interact with the environment to build up their mass. If we visualize with this very simple cartoon the density field, so this would represent a void. This is the mean density of the universe, and this is a very deep void. We can expect that galaxies that live here at the very bottom of the well of the density field, so at the center of the void, have different evolutionary path than the galaxies that live here, that are just below the median or just above the median or very much above the median. But also in this case, these three galaxies might have different evolutions, because this center of void, this well, is way closer to the mean density than the other one. But also these galaxies might have a different evolution. So at fixed depth inside the well of the galaxy the well of the density field created by the void, it will also be interesting to study the evolution of these galaxies that live inside the different kinds of void, but at the same sort of depth. So to do this, we did this exercise by choosing, we chose a tiny interval of redshift between 1 and 1.1, just to avoid being biased by the evolution also of the universe, which was a very small redshift bin. We plotted the correlation between the density of the density contrast of the galaxy at the bottom of each void with the size of the void in which they live. And the colors here is the stellar mass of the galaxy. So we chose galaxies that live at that have sort of the same mass, but that live at the opposite ends of this correlation. So galaxies that are in large and deep voids, and galaxies that are in small and shallow voids. And we did this test with the lower mass galaxies and higher mass galaxies, and we wanted to compare their merger histories. So here you're seeing the void, actually, the distribution of galaxies inside the voids, and the sphere is this very sized version of the void that identifies the radius. And this is the merger tree related to the galaxy that is at the top, at the bottom of the well of the void. And you can see that the galaxies in smaller and shallow voids have more mergers than galaxies that live at the bottom of deeper underdensities, so that they are more isolated, because the void has they are more isolated at the center of this underdensity. And this is the galaxies at lower mass, but the same can be seen in the higher mass case. So this galaxy, of course, had a lot of mergers, even if it was inside a void, but because its final mass is 10 to the 10.5, so it's the mass had to be built up somehow. So in both these cases, you can see that the galaxy in larger and deeper voids have more simpler merger history than their counterparts. So this is the recap of what I've just said. So this is the small and shallow voids, large and deep voids, and vertically you can see the low mass and the high mass. So the take-home messages are on the right side. So as I was saying, the galaxies in environments of similar complexities, galaxies build up more mass when they interact with one another, of course, but at fixed mass, galaxies have more interaction in shallower voids because they are closer to the mean density of the universe, so they are in shallower ponds than others. And to take this further, we also looked at the galaxies with similar mass at the extremes in terms of void size, not so at the same depth of the void. And we see the effect that in galaxies in large and deep voids, since they are more populated, they are bound to interact with somehow, even though not even just three mergers, they are bound to interact somehow with the environment, while galaxies in small but very deep, so very tiny but deep density field wells, they basically don't have mergers in their lifetime. So this is the summary of the results that I have just presented, and I will leave here with the next steps of this project, which is still a lot of work to be done. So, and we will, of course, we'll hope to apply all these analyses on observational data next year when we come. So thanks.